This video is all about composite functions. We're going to create some new equations. The two original equations we're working with are f at x, which is a parabola x squared minus 1, and g at x, a simple line x plus 1. We'll do 5 different questions. A is just add the two functions, f plus g at x, which is the same as f at x plus g at x. Do you have to write this line? No, I'm just showing you. This notation is the same as this. It's just add the two equations together. So add the f at x equation plus the g at x equation. Do you have to put g at x in brackets? No, but it'll help us later on. You'll see. Again, you could have gone right from this line to here, or even right from here to no brackets, since this plus doesn't really matter. Just rainbowing a plus in didn't matter. You could go right from here to here. But now you got to simplify. Well, that's pretty easy. X squared and x don't have any like terms, and minus 1 plus 1, those are like terms. Minus 1 plus 1 is obviously 0. So you're left with x squared plus x. And you could just leave it like that. I like to factor it though. You could leave it like that, you get full marks, but I'm going to pull out an x, and I'm left with x times x plus 1. Just check that. If you rainbow this x back in, you'd get x squared, and you get x. So there are the two functions added together. What happens when we have f minus g at x? That's the same as f at x minus g at x, or you can go right to, that's the same as the f at x function minus, this time you definitely need the brackets, the g at x function. The reason you need the brackets is you got to rainbow that minus in, or distribute it. So minus the x, you won't believe how many people forget to do that, and this one stays positive. It shouldn't be. It should be minus the x and minus the 1. When we simplify that, we'll collect like terms again. You get x squared minus the x. I just put the x squareds first, then the negative x. Minus 1 is minus 2. Again, perfectly reasonable to stop there, or you might pull out the fact that this is a nice quadratic that multiplies to negative 2 and adds to negative 1. What two numbers do that? Well, easy. It's just going to be negative 2 and positive 1. So you could have left it in standard form or factored it into factored form. X minus 2 times x plus 1. So we've added, we've subtracted two functions. Let's multiply two functions together. F times g at x is the same as f at x times g at x. Notice I didn't use a dot here. A dot means something else. So let's multiply these two functions. I'm going to put brackets here because you have to. X squared minus 1 times all of x plus 1. When we're multiplying these brackets, we'll distribute or FOIL. First times first is x cubed. Outside times outside is x squared. You could draw the arrows, but I'm not going to. I did this times this. I did this times this, the outside. Now the insides, negative 1 times x is negative x. And the last thing's negative 1 times 1 is negative 1. That's obviously a cubic. I'm not going to waste my time factoring it. Leave it in standard form is good to go. Now we want to do f divided by g at x. That's the same as f at x over g at x. Again, feel free to skip that line and go right to, that's x squared minus 1 over x plus 1. And you could leave it there. But we studied this in Unit 4, and this was rational functions. You should recognize that x squared minus 1 is a perfect square. So leave it there, full marks. Or notice this is the same as difference of squares. I'd watch the video on difference of squares if you don't know how I do this. X squared minus 1 is the same as x minus 1 times x plus 1 over x plus 1, and we covered this in Unit 4. And since we have a factor on the bottom, same as the factor on the top, we can cross it out, and we're left with x minus 1 with the restriction that x cannot equal negative 1. That comes from the crossed out factor. What can x not be in the denominator here? Can't be negative 1. So the equation, or the result of this simplification, is x minus 1, x cannot equal negative 1. The last new equation we're going to create is f at g at x, which is sometimes written f dot g at x. That's why back here in part C I said, notice this is a times symbol, don't use a dot. A dot means sub one function into the other. That is, f dot g at x would be f at g of x, sub g of x into f at x. So I should have an equal sign here. I'm going to move this e up here so that doesn't look confusing. So this is sometimes how the question is given, part e, which is the same as sub g at x into f at x. So here's what I'm going to do. I'm going to leave the f alone, f at, and I'm going to sub in g of x. That is, I'm going to replace the inside first. Your order of operations, do what's in the brackets first. What's g at x? X plus 1. I'm going to sub x plus 1 in for g at x. And now I want to evaluate f at x plus 1. So take this whole thing, x plus 1, and sub it into f at x. What I do is I leave the rest of the equation except the x. I'm going to put a bracket for this f at x is x, as in you're supposed to sub into this spot, square it minus 1. So sub into this spot, square it minus 1. Except this time I'm not subbing in numbers, I'm subbing in an x plus 1. This x plus 1 goes in this x spot. I get x plus 1 squared. Now here I can't really leave it. I should probably expand it to see if I can simplify a bit. So I'm going to expand this. So lots of students are going to just square the x, square the plus 1. Hopefully you know that's wrong. X plus 1 squared is the same as x plus 1 times x plus 1. That's a FOIL, or distributive, like we did in a previous question over here. It's first times first, x squared. Outside times outside. 1 times x is just plus x. Another 1 times x on the inside times inside. That's this times this. And the last times the last. That's a plus 1. And that was worth doing because you see this plus 1 and the minus 1 cancel out. And you get x squared plus x, that's plus 2x. Now you could leave it like that, or like in one of the early questions, that's part A, you can leave it as standard form or factor out an x and get x times x plus 2. Again, rainbow it in to see if you want that, yep, you got the right answer. So we created 5 new composite functions by adding, subtracting, multiplying, dividing, and by subbing one function into another.